Okay, there's two documents on Blackboard that you might want to open up and just take a quick glance through it before we get started working on them. One of them is a summary of the various tests. You also have that in the lecture notes, in the slides, talking about formulas you might use with a single sample t-test, with a t-test involving a proportion, with two sample tests where you're assuming the variances are equal, and another two sample test where you're assuming that the samples have different variances, right? So there'll be a number of formulas we're going to play around with. But once you understand the problem, read the problem and understand the problem, it's going to be your next challenge is going to be to interpret which of those formulas to apply, which of those forms of the t-test to apply. Okay, so what is the t-test doing? What the t-test is doing, it's testing whether or not the means of one sample or one sample and a value or two samples, whether or not they are far enough apart that you can say with some level of certainty that the means of the population that those samples are drawn from are really different, right? In other words, what we're testing is we don't really care about, well, in a sense, we don't really care about the means of those two samples. What we really care about is the means of those two populations. If it's a drug test, the means, the mean, let's say blood pressure drug, the mean blood pressure for all those individuals that might take the control, an entire population that might take the control substance versus an entire population that might take the actual drug and the effect on their blood pressure. So we're comparing those two means, but we don't know the population means, so we have to rely on the samples instead. So since we're relying on the samples, there's some uncertainty. We want to make sure they're far enough apart to be able to say that they're really different, and that the difference isn't due to chance. If you sample the same population, no difference, you sample them twice, most likely you're going to get a different answer each time you sample it. If I took this class and sampled five people, asked five people what their age was, took an average. If I blindly went back and randomly took five people and asked for the average age of those five people, even though it's one population, it's unlikely I'd get the same answer twice. Now the question is, obviously in that case, I got the answer. That difference in the answers was just due to chance. It wasn't due to a real difference in the mean population age for this class. So that's what we want to avoid. We want to know that we want to know to a certain level of certainty, usually 95% certainty, that when we say that those two population means are different, that difference that we've determined wasn't due to chance. It was due to a real difference in those populations. Okay, so that's what we're going to do. And generally, we do that by using our understanding of what the variability in the numbers is. In other words, we're not going to say that we're satisfied when the blood pressure is 10 millimeters of mercury different. We're going to say that we're going to be satisfied when the difference is two standard deviations different, or maybe 1.96 standard deviations, depending on how accurate we want to be. Okay, so we're going to use standard deviations to determine the difference. How do we calculate that? Well, we calculate the difference in the two means, and we divide by what the standard deviation is. So we get a number, z-score or t-score, which is really kind of the number of standard deviations apart the two means are. And if there are enough standard deviations apart, then we figure that that's not going to happen very often. So we reject our null hypothesis that the two population means are the same. So let's go through all the different, as many of the permutations as we can now of how we might get data that we might have to analyze. So you got two documents. One is that PDF document with a whole bunch of formulas listed in it. Let me see if I got a copy of it open here. First, let me get rid of that. You don't need to see that. Here you go. There's a whole bunch of formulas here. Whoops. Some reason it's not blowing up when I click the, how about view? Zoom. Okay, control. Let's do that. Nope, that's not working either. That's interesting. Whatever reason that's, oh, there we go. Just slow. Okay, so we have a document that's going to give us a whole series of formulas. But let's go back and let's look at each one of these cases individually. We have an exercise, single sample hypothesis test. Okay, and let's take a look at this exercise to start with. We know that, for instance, single sample hypothesis test, where we know the standard deviation of the population. Okay, let's say that this is our sample. We take 9 individuals, we take a measurement, we have 9 numbers. We know the standard deviation of the population that it's drawn from is 3. We're told that maybe a previous very large study that we have some justification for assuming that, and we're going to test it against another population whose mean is known to be 8. So we want to know, is this population's mean different than 8? So what's our null hypothesis going to be? Anybody want to propose a null hypothesis? Right.
Population.
The two means are the same, right? That the mean of population number 1 is equal to the mean of population number 2. Okay, what's our alternative hypothesis? Well, actually, wait a second. We know what the population of number 2 is, not what the mean of number 2 is. It's equal to 8. So I can just simply put 8 in there. So what we're saying is, our assumption is, null hypothesis is that the mean of our population number 1 that we've sampled, we don't know its true population mean, is equal to to 8, which is the mean of the other population. Our alternative, let's for the moment say we're just going to deal with two-sided hypotheses right now. It's going to be mu1, whoops, mean of population number 1 is what? Not equal to 8, right? You could have just easily stated it as not equal to mu2, but we know mu2 is 8 in this particular case. Okay, normally we won't, but this is a single sample test. Okay, so how are we going to do this? Well, let's get Excel up, and I think I gave you, if you go to Blackboard, you can either type, there's only 9 numbers. You can either type them into Excel, or you can open up a version of it that I've given you. Uh-oh, I got to mute somebody. I can tell. I think we're okay now. Okay, good. Okay, so let me zoom into this. Okay, and I think I gave you, let's see if I've got it here, single sample test. Okay, that look like the same numbers. I'm going to get rid of these numbers for the moment and come back. So hopefully these numbers match. Okay, 5. Oh no, there's a mistake in here. 5, 5, 7, 9, 5, 7, 8, 9, 10, 11, 12, 13, 14. Not a very normal looking distribution, but from the sample anyway. But let's leave it with what we have. Okay, so what's the mean of this sample? Mean's going to be equal to the average of these values. Okay, 9.8, 8, 9.9. Now, we don't know the standard deviation. Well, we do know the standard deviation for this population. What's the standard deviation for this population? In other words, sigma, right? We said it was 3, right? That's known. Okay, so what's our standard error equal to? Our standard error is equal to the standard deviation divided by the square root of the sample size. What's the sample size? 9, right? Okay, so divided by 3. Okay, so the standard error is equal to 1. Okay, so now, if we were going to look at our formula, what is our formula going to look like for our z-score or our t-score? Okay, first of all, what am I going to be looking for here, a z-score or a t-score? Z or t?
T.
You know, you can never be wrong by using t, can you? However, in this case, we happen to know, a very unusual situation, we happen to know the population standard deviation. So we don't have to account for that extra level of uncertainty that we would be introducing if we were dependent on the sample to give us our standard deviation. We actually know the standard deviation for the whole population. So I'm going to assume for this moment, for this particular first example, that we're going to actually calculate a z-score. And our z-score is going to be equal to the difference between the two means, mu1 minus mu2. Or in this case, mu1 is 9.9 minus 8 over the standard error, which is 1. Okay, and if I resolve that, let me actually copy that out. Okay, it's going to be equal to 1.9. Okay, so now in order for me to be 95% certain that there really is a difference between these two, with a two-sided test, I have to go back to my distribution, my sample distribution, and say to myself, well, my expectation is, whoops, loosen up here. Yeah. My expectation is that the way my samples would be distributed, that if this is the real mean, right, that 95% of the time that I would have a sample of size 9, n equals 9, right, and sigma is equal to, what was sigma equal to? 3, I guess, 3, right? Okay, 95% of the time, if I took a sample of this size, right, that I would be within 2 standard errors, 1.96 standard errors of our actual mean. Okay, so that 2.5% of the time that I might get a lower, by chance, get a difference that's greater than negative 1.96 or less than 1.96 or greater than positive 1.96. But that would only happen very rarely, less than 5% of the time. In other words, we'd have an alpha error less than 5.05, right? We'd be 95% certain. So if I take a sample of size 9 and I get a result that's outside of this standard error, number of standard errors, or above this number of standard errors, that would be expected to occur less than 5% of the time by chance alone. Okay, so I'm going to say I'm willing to take that risk. Take that risk. I could be wrong 5% of the time because the difference is really due to chance, right? And say to myself, as long as my z-score is either smaller than 1.96 or greater than 1.96 plus 1.96, I'm going to reject my null hypothesis and say the difference is a true difference in the means, not because it's due to a chance in the way I sampled it. Okay, everybody got to have can everybody agree with that, right? So what did we get when we did it ourselves right now? What was our result? How many standard errors apart were they? Right, where did my Excel? 1.9. So is that far enough apart for us to say that these are different, that the result is not due to chance? No, it's not. Right, it would have to be greater than 1.96. Okay, so now I'm going to change one of these numbers. I'm going to make this number 18. Okay, and this time I got 10.3 as the mean for my sample population. And let's see what I get for my z-score now. Okay, now I get a z-score of 2.3. Can I reject the null hypothesis now? Yes, I can, right? So what does that make that 1.96? That makes that 1.96 a really important value for us, right? What's another good name for an important value? Critical value. That's our critical value. That's what we need to exceed in order to reject our null hypothesis. So if our value exceeds 1.96 of our z-score or t-score, whichever one it is, exceeds the critical value, that's the same thing as saying that result has less than 5% chance of occurring. That big a difference has less than 5% chance of occurring by chance. Right, so it's more likely than not that's going to, it's at least 95% certainty that difference is actually due to a difference in the two population means. Less than 5% chance that it's. And now, do we know how much less? Well, in the case of the z-score, we do know what the percentage is, right? Because we can go to the z-table and look up what that probability of getting that big a difference is, right? I could actually go to the z-table, and I'm just going to do this here because when we go to the t-score, we're not going to be able to do it, and we'll talk about why we're not going to be able to do it. Oops, that's t. Do I have a z-table here? Oh. Okay, I'm going to look at 1 point, what was it, 2.3? 2.30. There's only about a 1% chance on that lower tail and a 1% chance on that upper tail of getting a value that far apart, right? So that's the probability on each tail is 1%. On the lower tail, it's 1%. If I went to 2.3, it'd be 99%. It'd be 1% on both ends. So there's only a 2% chance of getting an outcome that has a difference of 2.3 standard errors apart in those two means, right? So that means that my real probability of being wrong, if I reject the null hypothesis, is not just less than 5%, it's 2%. We can use the z-table to tell us what that is. Now, when we're doing the t-test, we don't have a table like this. We would need a table like this for every sample size in order to be able to use the t-test that way. Instead, when we do the t-test, oh, I got to go back. Somebody else got their mic on. I can hear it in the background there. Okay. When we do the t-test, right, all we have now is we have a critical value. All we have now, if that sample size were 9, if we were doing a t-test, we didn't know the population standard deviation. We couldn't use 1.96 as our critical value. What would we need to use as our critical value now? We'd have to use 2.3 as our critical value. And if we exceed 2.3, we know there's less than 5% chance of being wrong. If we don't exceed it, we know that there's a bigger chance of being wrong than 5%, which we don't want to tolerate, so we don't reject our null hypothesis. We fail to reject our null hypothesis, right? So the t-value tells us that's our marker, that's our critical value, that's our decision point. That tells us when we have less than a 5% chance of being wrong when we reject the null hypothesis. However, if I gave you a value, if the difference was 2.46, a t-score of 2.46, there's no t-table for that specific sample size that I can go to look up the exact precise value. Okay, not so true with our software. When we use SPSS, we're going to play around with SPSS a little later on. SPSS will actually have a t-table built into it, like a z-table, for every value of sample size. It has it built, so it'll actually give us a p-value, probability of being wrong, so we don't have to just guess at that, just say that it's less than 5%. You could kind of bracket this a little bit. If you look at this, if we were willing to accept a 5% chance of being wrong for a sample size of 9, we would have degrees of freedom 8. We would have to exceed 2.3. If we wanted to be 99% certain, have an alpha error of 1%, then we would go over to this column, right? 99%, less than 0.5% in each tail, right? We would have to go here, and we would have to have a t-score of 3.4 that we'd have to exceed. That would be the critical value if we wanted to be 99% certain, have an alpha error of less than 1%. Okay, so if we have a t-score if we determine our t-score is 3.1, we know that our level of certainty is between an alpha of 5% and an alpha of 1%. You can kind of bracket it based on what you see there. Is anybody going to ask you to do that? Most likely not, but you never know what's going to turn up on a test, right? Okay. So that makes sense to you? That like it's kind of you can determine by using this table. It won't tell you exactly what your probability is, that your p-value is of being wrong if you reject the null hypothesis, but you can kind of bracket it and decide whether it's between 90% and whether it's 10%, 5%, 1%, and so on. Okay, so, okay, good. Let's move on to the next problem. Okay, now in this case, sigma is not known. Same problem exactly, except this time sigma is not known. Let me go back to this value. Let's see, and I think we kind of just figured out how that affects things, right? I'm gonna go back here. I'm gonna change this to. I'll leave it the way it is. I'll just change it to 17 or 16. Okay, that comes out to 10.1. Our z-score is going to be equal to, well, now standard deviation. I don't know the standard deviation, do I, for the population? I have to calculate it now. It's not going to be sigma. I have to go ahead and calculate it. Okay, it's going to be equal to the standard deviation of all of these numbers. And the standard deviation comes out to be 3.3. Okay, it's a little bit different than what let's say, for instance, that the population really was a standard deviation of 3. Why is it different? Because it's a sample. Every time I take it, every time I get another 9 numbers, it's going to be a little bit different. Sometimes be under 3, sometimes be over 3. But that's part of the reason why we have to use a t-score instead. So now my standard error is going to be 3.33 divided by 3, but divided by 3 because sample size is still 9. So my z-score now is going to be 10.1 minus, okay, 1.11. Okay, and we should actually really copy those values into a new formula, but I don't want to kill too much time here. Oops, excuse me, that's the minus. We're comparing it to the number 8, right? 10.1 divided, that's divided by 1.11. Okay, let me copy that and plug it in here. And my t-score now comes out to be 1.89. Okay, I don't even have to go to my t-table because I know that not only have we not exceeded the critical value of t for 8 degrees of freedom, we haven't even exceeded 1.96. And the t-score is always going to be more than that, 1.96. Right? The z-score is kind of the t-score for an infinite sample size. So I know I'm not going to be able to reject my null hypothesis. The big difference here was that I could, if I knew what the population standard deviation was, I could use the z-score. If I didn't, I have to use the t-score. Almost always in real life, we'll be using the t-score. Yes?
Okay, so for these problems, the endgame isn't actual defined t. It's just to compare the z-score to the t-score. So the critical value of the z-score and t-score.
I'm sorry, back up again.
So we don't actually define t. We're just taking the t-score and comparing it to whatever the 1.9.
Oh, you don't actually. You're right. You don't. If your concern is only to decide whether to reject the null hypothesis or not, if your only concern is whether or not there's a greater than 5% chance of being wrong if you reject the null hypothesis, no, you don't need to know what the p-value is. However, it's always nice to know that because that's more evidence. If you can say that, in other words, if you read an abstract, right? If they get a p-value of 1%, they're going to brag about that. They're going to mention p equals, 0.011, 0.011 or something like that. That they demonstrated this to a level of certainty greater than 95% or with a chance of being wrong of less than 5%. So you're going to want to, highlight that, right? Now, of course, if it turns out to be 4.99, right? A 0.0499, you might not brag about that. You might just put the critical value, might put that it was significant at this level or something like that. But yeah, sometimes you might want to know that. You might want to evaluate what your levels of certainty is. Okay. All right. And in fact, if you're, also a lot of times you may wind up publishing and you haven't reached the point where you can reject. Like just now, we got a t-score of 1.89. Now you might wind up publishing this. So just saying you didn't reject the null hypothesis is not going to be enough. You're going to want to tell them what the probability was that the result or the difference was due to chance. And in this case, maybe it happened to be 6% chance of being due to chance. So that might be valuable to know at some point. Okay, so let's go on to the next possible situation. A 2-sample t-test with equal variances. Well, first of all, how do I know the variances are equal here? Do I know the population? Is there anything here that you see that suggests that we know the population means for males and females, or that we know the population standard deviations for males and females? No, it's not a word problem, but we can see the numbers that we've gotten. Nobody has given us any information about any of the population. What are they called? Not statistics, population parameters, right? Parameters are the true mean, the true standard deviation of the whole population. The mean and the standard deviation of a sample is the statistic, right? So we don't know any of the population parameters. All we know is the population statistics, right? Which is what we drew from these samples. How many people are in these samples? 3, 6. What a coincidence! It's 9 again. Okay, so now let's take a look at this. Now, first, let's go to that chart that we just had, or maybe even the lecture notes. Let me see if it's on the chart. And if I can't find the chart again, where did I put it? PDF file, Z table. Here we go. Okay, okay. So, standard deviations, sample standard deviation is assumed to be equal, right? Okay, that's our case here, right? Well, we don't know that yet. Tell you what, before we assume that, let's open up. Let's put those numbers into Excel. Let's see, Excel to sample t-test. I think that's them there. Okay. Okay, I'm going to make that even a little bit bigger. There we go. That's bigger. Can you see that well? Yeah. Okay, well, you got it on your machines too, presumably. I'm just going to go back and just make sure that, like, the numbers I put up here are the same as what's in my document, because what happened, when I do this sometimes from semester to semester, you just saw me change all the numbers, right, to demonstrate something, and then, like, I change it. I save the file, I don't change it back. Yeah, it looks like the numbers are the same here. Okay, let's calculate the means and standard deviations for both of these samples. Okay, so X bar. Okay, X bar 1 and X bar 2. Okay, mean is equal to average, parentheses, of these numbers. So the mean of this group is 10, males is 10, and I'll just copy this over. Fill left. Oops. Oh no, I went the wrong direction. Fill my other left, which is my right. Okay, and this is 7.5. Okay, that's the difference in the means of these two samples. Let's find the standard deviations of these two groups. Standard deviation 1, standard deviation of group 2 is equal to standard deviation, parentheses, okay, 2.7 equals standard deviation of this group. Okay, it's about 1.94. Now it's going to be kind of tough for us to make a judgment on this. One of the ways you might look at this, you might say to yourself, if the standard deviation of one group is twice the standard deviation of the other group or more, maybe you'd be a little bit uncomfortable about saying that they're equal standard deviations and pooling the standard deviations. First of all, why would I want to pool the numbers to make a standard deviation anyway? Can you think of any reason I might want to pool it? Yeah. Yeah, if you have a small sample size. In other words, I'll get a more accurate if in fact, a lot of times you'll measure something in one population, something in another population. The means may be different, but the amount of variability very often is the same. So it'll have the same standard deviations. And you'll have a much better estimate of the standard deviation if you can assume that it's based on 18 people instead of 9 people, right? So there is some value to doing that, especially if you have a small sample size where we're comparing a group that has only 3 or 4 people or 5 people versus a group that has 30 people. But we have some reasonable expectation that the variability, even though the means may be different, that you even might not have a reason for the variability to be different. So yeah, there's a good reason to want to pool these things. Okay, so now let's take a look at how we're gonna deal with this stuff. So we're going to assume that, yeah, a little bit of a difference, but I'm going to assume that they're equal. Okay, so now let's take a look at what our formula is going to look like. Okay, well, in order to solve this, right, we're going to calculate a pooled standard deviation. Actually, using pooled standard deviation. S1. Oh yeah, this is got. It should be SP squared over the two. You see over here the S1. That should say a P in there. That's the pooled standard deviation, right? Pooled standard deviation over n sample size 1 plus pooled standard deviation for sample size 2. As it happens in this case, that the sample size is the same in both of them. So it's the these really would wind up being the same two values added together. Okay, so let's give that a try. Let's calculate the pooled standard deviation. Okay, so pooled standard deviation is going to be equal to the sample size minus 1 times the standard deviation squared. Anybody remember what the standard deviation squared is called? That's the variance, right? Okay. All right, so let's see if I can't get these to show me both the formula and my spreadsheet at the same time. So I'm going to calculate SP. Oops. Okay, standard deviation pooled. And that's going to be equal to the square root of, okay, so now it's going to get a little complicated here, right? N minus 1 for the first group is 8, okay, times the standard deviation of group 1 squared. Okay, so here's group 1, right? Whoops, forgot to put an equal sign in there. See if we can do this without messing it up. Okay, 8 times 2.7 times 2.7. Okay, that's the standard deviation squared. Plus N2 is 9, that's 8. Put that in front, 8 times the standard deviation 2 squared. Oops. Asterisk 1.9 times 1.9. I'm going to close these parentheses. I got the top. I'm going to put all that over. Well, first I'm going to put it in another set of brackets. So it adds those two parts together before it does the division. And then I'm going to divide by n plus 1, n1 plus n2 minus 2, which is 9 plus 9 is 18, minus 2 is 16. And I'm going to cross my fingers and hit enter. Anybody think that's going to work, right? Okay, everybody have some level of confidence going to work? Okay, so here's our pooled standard deviation. Pooled standard deviation is equal to 0.6, basically. Okay, so now I'm going to calculate, I'm going to use that, my pooled standard deviation, in this formula down here, and I'm going to calculate my t-score. So now let's do that. Let's calculate our t-score. I'm gonna do this in 2 steps. I'm going to calculate the numerator first, which is x1 minus x2. So I'm going to take the bigger number minus the smaller number, just to make it convenient. 10, whoops, equals 10 minus 7.55. I'm going to divide that by this value. That's going to be equal to the square root of, let's see, our pooled standard deviation over sample size 1, which was 9, plus our pooled standard deviation over sample size 9 in the second group. Okay, and I'm going to hit enter. And so my t-score is going to be equal to the numerator divided by the denominator. It's going to be equal to 2.44 divided by 0.36, and it's going to be equal to 6.73. Now I'm going to check that in a second. Obviously, that t-score suggests that there's very little chance that these two are from the same population. That was the square root. Did I take the square root? I did take the square root. The square root of the pooled standard deviation. Did I square the? I didn't square the standard. Well, yeah, I didn't square it, did I? Okay, hang on a second here. We got to go back in. We have to go back in again, as the surgeons say. You know, when you're watching on TV, right? They always leave something behind and you have to go back in.
I got a different.
Oh, no, don't tell me you got a different answer.
I did it twice.
Hang on a second. Yeah, well, I didn't square the standard deviation. The pooled standard deviation. Hang on a second. How can I get in here now? Okay. Okay, hang on a second here. Okay, let me think about whether this is going to mess up or not. No, it should. This should work. I think this will work. Oh, no.
I was going to say there's a multiplication.
Yeah, okay. So first I got to do this.
I forgot.
You forgot to square it also?
I forgot.
Oh, yeah, I forgot. I didn't put in the D14 again.
I
Okay.
got 2 points.
It's, I listen, we're going to do this again on the computer behind me on the PC. I don't have, unfortunately, for some reason they've had it's been hell for me trying to get SPSS installed on my machine. We're going to do this again using SPSS to compare our answer number one and also to see how we would resolve the same problem in SPSS. Okay, so let's see. Does that look right? Anybody want to object to that before I hit enter? That looks okay to me, I think. Right? Squared, this is the pooled standard deviation squared divided by 9 plus pooled standard, and then the square root of that whole thing. Oh, jeez. That doesn't look right to me.
Yeah, I just it's
Times.
0.59. I don't
What?
know.
What's that?
It's the 0.59. I don't know.
Oh, the 0.59? Hang on a second. Let me make sure we got that right.
Wouldn't it be like somewhere between the standard deviation of the two substances?
Yeah, you would think, right? Let's see.
I got 3.3.
You got 3.3?
It's 7 o'clock.
Where did I make a mistake?
Wait, you got the same thing?
Okay, hang on a second here. Let's see. 8. You got 8 times the first one squared, right? 815. Okay. And 8 times that squared, added together, divided by 16. Yeah, I'm having the same problem here. Let me copy this again so I can paste it in here. What's that? I'm missing a parentheses at the end? Oh, I got you. I got you. I'm just squaring this taking square root of the top. You're right. Yes, you're absolutely right. Parentheses there, and I need another parentheses up here. Well, this is a good argument for doing this. There you go. How's that? Better? Okay. And, okay, so I'm going to assume that the second part of this is right, and my t-score comes out to be 2.74. Okay, can I reject my null hypothesis? Well, what do we need to know now? What's our critical value, right? How do we determine what our critical value is? Well, in order to determine our critical value, we have to know our degrees of freedom. So for this particular situation, 2 samples, right? How do we calculate that we're pooling our values for our standard deviation? How do we calculate our degrees of freedom? Well, it's a sample size 1 plus sample size 2 divided by 2, which is 18 minus 2, which is 18 minus 2. So our degrees of freedom is 16. So now how do I find out my critical value of t that I have to exceed? I have to determine whether 2.74 is correct or not. And we're going to go back and have to look at that and see if I calculated correctly anyway. Okay, so how would I know that? I go to my t table. Okay, let's see. Where is it here? It's definitely here. Okay, oh, that's my z table. Here we go. Okay, so for 16 degrees of freedom, what's our critical value of t? Right, 95%, 2.5% each tail, an alpha of 0.05%. For a degrees of freedom equals 16, our critical value of t is 2.12. Have we exceeded 2.12? Yes, we have, right? Okay, in fact, I'm going to go back and check right now because we are in agreement. We are in agreement in the first part here. Before we go on and actually compare this, right? We're in agreement that our pooled standard deviation is 2.37, right? You caught me on my missing parentheses there. Now our denominator is going to be, I think, did we get that right? Yeah, once I changed that, it should have made everything right. Except now I got to do the same thing here. Correct? Had the same problem here. Got to be the square root of this the whole thing. See what that does. Oops. Okay. So now that changed things, didn't it? Right? Okay. 1.19, and our denominator denominator is 1.12. Divide our numerator by a denominator, it comes out to a t-score of 2.18. Assuming that I haven't made any screwed up anything else, right? Okay, with our parentheses. Our t-score is 2.18. Did we exceed our critical value? What was our critical value again? Anybody remember? 2.1. It was 2. Was it 2.12? Well, you people have worse memory than I do. 16. It was 2.12. Very good. Exactly right. Yeah, 2.12. And what did what was it? 2.18. So I've exceeded my critical value. So what's the probability that we would get a result of these two means being that different by chance? How often would that happen? What percentage of the time? Less than 5% of the time we would get that big a difference by chance if the means of these two groups were different. So at a level of alpha equals 0.05, we can reject our null hypothesis. There's less than 5% chance that we would be wrong if we did that. Okay? Is everybody comfortable with that? And now we can take a look at the easy way to do this. Okay? And in fact, you could do it both ways. You could do it in Excel by hand. And then if you have the data, you can do it in SPSS as well. So I'm going to switch over to the other machine. Okay? And I'm going to do this way. Let's see if this works. Okay, you guys online are okay? Oh, good. I had a whole bunch of suggestions here online. Sorry about that. Okay. Are you guys satisfied online that I did it right? Okay, good. They're happy. They've been checking me. Okay, so now what I'm going to do now is I am going to switch over to the other screen. So I am going to go in here and I'm going to make the other guy, the other computer the presenter. Okay.